Acid-base titrations. This is the last topic of this semester. Acid-base titration is a lab technique. It is a procedure used to determine the concentration of an acid or a base solution. We may not be familiar with the name or the technique. However, we know almost everything about the chemistry applied in this technique. So basically, the concentration of an acid or a base solution is decided by this reaction. What is this? A neutralization reaction, a reaction between an acid that supplies protons and a base that supplies hydroxide. This is basically all the chemistry involved in this technique. How? Well, let's move on. It is a neutralization reaction in which a measured volume of an acid or a base of known concentration, so a measured volume of something of known concentration, completely reacted with a measured volume of a base or an acid. If you're using an acid here, it's going to be a base here. If you start with a base here, it's going to be an acid of unknown concentration. How can that be used to decide the concentration, the unknown concentration of a base or acid? Well, let's move on with an example here. Let's assume we are using an acid with known concentration to decide the concentration of unknown base. Let's say here we're using a base. So what we would do is that we're going to use an acid with known concentration molarity. So let's say we know the molarity of the gas acid. I'm using lowercase a to represent. That's the concentration of the acid solution. So we know the concentration of acid. Then we're going to react some volume of this acid with some volume of the base with unknown concentration. Well, so we know, number one, we know Ma. Number two, we know the volume of the acid reacted. We also know the volume of the base, a measured volume of a base. We also know the volume of the base reacted with the acid. We are trying to figure out what is the concentration of the base. So basically, so far, those are the information we know from the description here. With this titration technique or procedure, these are the information that we have, and that is the concentration we're trying to figure out. How? With this information we have, how can we get the concentration of the base? So let's move on again. For a strong acid-base reaction, for a reaction between a strong acid and a strong base, the protons supplied from the acid and the hydroxide supplied from the base, they react in the 1-to-1 ratio. All the moles of proton will equal the moles of hydroxide. They are reacting in 1-to-1 ratio. Well, how can we get the moles of protons, the moles of hydroxide? How do we translate this equation into an equation that all these variables are involved? How can we do that? Well, do you remember the definition of the molarity of something? We know the molarity of acid and we want to know the molarity of the base. So what is molarity? Do you guys still remember? Molarity equals moles divided by the volume in liters. So if we know the molarity, if we know this one, what do we know? We will know the moles of acid or base. For example, right now, if we know the molarity of acid, volume of the acid, then the moles of the acid is molarity times by volume, which is also true for base. Moles of base will be molarity of the base times by the volume of the base. So far, so good. However, be very cautious here, because here is the moles of the acid. We're using acid as an example right now. What you have here is the formula to get the moles of the acid. However, moles of acid may or may not be the same as the moles of proton. Here is our goal. Why? Because an acid could be monoprotic, could be diprotic, let's say hydrochloric acid, sulfuric acid. So depending how many protons can each acid molecule supply, the moles of protons, let's focus on the protons right now, hydroxide is the same. Moles of protons will equal the molarity of the acid times by the volume of the acid, which is this one, multiplied by I. I is the number of protons or base, hydroxide, supplied from each acid formula. Are you guys following me? If each acid supplies only one proton for a monoprotic acid, the moles of protons will be the same as the moles of acid. However, if each formula or each molecule of the acid supplies 2 protons, I will equal 2. Does that make sense to you? Now you're going to use this. So if moles of hydrogen will equal moles of hydroxide, then M, molarity of the acid, times by the volume of the acid, multiplied by the number of protons supplied from each acid molecule, will equal the molarity of the base times by the volume of the base times by the I, number of hydroxide supplied by each base formula. This is the moles of proton. This is the moles of hydroxide. Now, IA, IB, you know them from their formulas. As long as you know the formulas, you know the I. In this case, in our example, we're talking about using acid to titrate base. We know MA, we know VA, all the I's are known. We also know VB, which is here. Then MB is the only thing that is unknown. We know we can solve that. Does that make sense to you? All right, let's move on. Well, this is the titration setup. So what do we have here? In the beaker, we can place either a base or acid with unknown concentration, the solution that needs to be titrated. Okay, let's assume inside here, let's assume this time it's the acid whose concentration is unknown. So this acid has a molarity of Ma, which is the one we need to determine. Well, you place this acid solution with a known volume. So Va, the volume of the acid you place in this beaker, is known. So you measure certain volume of the acid with unknown concentration and pour it into that beaker. Inside this spirit, you add a base with known concentration, and you turn the stopcock, open the stopcock, you start adding base to it. At the beginning, when you add the base of known concentration, you read the initial volume. Let's call it volume 1, the first reading. Then you drop the liquid, the base into the acid. While you're dropping, you shake the flask. Let the reaction keep going. Once the reaction is done, once the amount of acid and the base totally reacted, you stop the stopper. Now the surface of the inside the liquid drops to here, for example. You read the volume again. That's volume 1. That's volume 2. Now the difference between these two readings, okay, volume 2 minus volume 1 is actually the volume of the base used to react with the acid in the flask. Does that make sense to you? So we know this, we know that. This is the only one that is unknown. All right, if you understand what is going on in this lab, let's look at all the information we just summarized on the last slide. Let's review it quickly again. So the key is that moles of protons will equal the moles of hydroxide when they completely react. We know that. Moles of protons equals the molarity of the acid multiplied by the volume of the acid solution times by I, and I is the number of protons provided from each acid molecule. Moles of hydroxide equals Mb times Vb times Ib. Again, Ib is the number of hydroxide provided from each base molecule. Well, moles of protons equals the moles of hydroxide. That's the equation. Now, in this case, in the case we're doing in our example, on the left, the one we're trying to titrate was acid. So Ma is what we need to decide. We know Va, we know Ia, we know Mb, we know Vb, we know Ib. All right. Everything's known except Ma. We know we can solve it. To solve it, you divide both sides by Va times Ia, Va times Ia, canceled. On the left, Ma is left. That's what you want. Equals Mb times Vb times Ib divided by Va times Ia. That's it. Now all the variables on the right, you know them. So plug all the numbers in. If you know, then you get Ma. Does that make sense to you? Well, it does. However, I do have a question. I don't know if you guys have a question for me or not, but I do have a question for you guys. While we were talking through the procedure doing this experiment, I kept saying you are going to stop the stopper when the reaction here, the reaction between the acid and the base, when it is complete. At that point, you need to stop the stopper. Otherwise, you'll be adding too much acid or base. Make sense to you? Now, here's my question. How do I know? Remember, here inside is a water solution. And how do I know if the acid-base reaction in that solution is exactly complete? How do I know that? In other words, how do I know when I should stop the stopper? Make sense to you? Well, luckily, no one can tell that actually. Luckily, there is something else that can help you or help us to make that decision. We are going to, in addition to the acid or base in this flask, we are going to add something else. That something else is called an indicator. An acid-base indicator is a compound that changes colors depending on the pH of the solution. When the pH is acidic, it shows one color. When the pH suddenly changes to basic, it turns into another color. So how do we utilize this unique feature? So an indicator is selected that changes color at a pH that corresponds to nearly as possible to the pH of the completing point of the titration. Here is a drawing that we can use to go through how an indicator works. Here, assume we have some base in this solution, and this indicator inside the basic solution, it shows yellow color, or yellow in acidic solution. All right, this is acidic. Let's assume inside the yellow beaker, inside here is acidic right now, and it says yellow in acidic solution, and we add some indicator to it. The solution is yellow. Then we start the stopper, drop in basic solution, they will react in the solution. While it is reacting here, when it keeps dropping into the solution, they're reacting, this solution pH is increasing because initially it was an acid and you are adding base to it. Base will consume the acid. At a certain point, assume at certain points you added enough base to the solution, it is complete. At that point, one more drop to the solution. We're on the last picture now. One more drop into the solution will make the solution basic, because when the reaction is complete, it is neutral. One more drop of the base will make the solution basic. This indicator under basic condition is red. So the solution will turn red. Once you see the solution turn red, you stop the stopper. Does that make sense to you? You may want to ask, wait a minute, if that is the case, that means you added one more drop to the solution beyond the completeness, the completing point of the neutralization reaction. That is correct. However, that one drop will not make a difference because you're going to use quite a few milliliters, hundreds of drops. So that one drop is not going to make a difference. Did I make this whole process to you? I'm sorry, did I make this whole process clear to you? So you use an acid-base indicator to help you to decide when to stop the titration process. All right, that's basically all for today. Not all, I'm sorry. All for this semester. However, we have one more practice to do. For the titration of sulfuric acid with sodium hydroxide, how many sodium hydroxide would be required? How many moles of sodium hydroxide would be required to react with 1 liter 0.5 molarity sulfuric acid? That's sulfuric acid. I equals 2 for sulfuric acid. Each molecule can supply 2 protons. Well, what is asked is moles of sodium hydroxide. Moles of sodium hydroxide will equal the moles of hydroxide ion. Does that make sense to you? For sodium hydroxide, I equals 1. So the number of moles of sodium hydroxide is the same as the number of moles of hydroxide ion. Each formula supplies only one hydroxide. Therefore, moles of sodium hydroxide in this case equals the moles of hydroxide, and we know in the titration reaction, moles of hydroxide will equal the moles of protons supplied by the sulfuric acid. Moles of protons equals molarity of the acid, volume of the acid, I, the number of protons supplied by each acid formula. Molarity is given 0.500. Volume is given 1.00 liter. Luckily, what is given is a liter. If not, we will have to convert the volume unit to liter. But in this case, it is liter. Good. 1.00 times by 2, I equals 2. It is a diprotic acid. Final answer, 1.00, 3 significant figures. All right. Good news for you. This is the end of this semester. Good luck to everyone. Bye-bye.